We've already seen different types of gradients and matrices involving derivatives. Now we're going to look at something a little bit more general, and it's referred to as the gradients of vector valued functions. So vector valued means that the input is vector valued. It's a vector of inputs, and we want to know the gradient of each one of those functions. So there's nothing terribly new here from the previous lesson. We're going to just generalize and see some new notation that's very common and that is more often used than some of the notation that we proposed. So suppose we have a series of m functions. Okay, so we're going to label those f sub 1, f sub 2, all the way up to f sub m. So these are just functions. These are just different functions. The reason we're using subscripts is just because we could have more functions than there are letters in the alphabet, and therefore we would, well, run out of function names, but this way we don't. So we have all these functions, and each one of those functions is going to input n variables, x1, x2, all the way up to xn. Okay, so m functions with n variables. So first of all, let's define what we mean by vector valued function. So here we have a vector of functions, each of which inputs a vector of values. And the way we could lay out each of those functions, or one way to do that, is to basically list each function going down the rows. Okay, so f1 will be the first function in this vector here, and then f2, and then all the way down to fm. So we're just stacking all of our functions in a column. Now this is an m by 1 vector because we have, again, m functions, one column. Each of those functions, however, inputs a vector. And that vector x can generically be written as a column, an n by 1 column, x1 all the way down to xn. So nothing vastly new there. So for instance, I could say f1 of x. I could actually rewrite that and say, well, what that really is in terms of scalars would be f1 of the vector x1, x2, down to xn. Right? So it could look like this. So it's a function, it inputs a vector. It could just be a matrix transformation where the output is some matrix times this vector. There's lots of different functions that we can apply. And then similarly for f2. Now, keep in mind, this is just one component here. So we are thinking of this as one. Okay, so the question we might have is, well, what would be the derivative of this vector of functions with respect to the vector of variables? Well, the way that we is, first of all, if I just look at the derivative of f1 with respect to that whole vector. So what I'm trying to do here is break this down into the smallest level that I possibly can, meaning that we've got all these vectors floating around. We have a vector of functions and a vector of inputs. So I'm going to convert the vector of functions into individual functions, each of which has a myriad of inputs. And the way that we've seen this is we're going to actually create a vector of outputs, right? Because the derivative of this function with respect to the vector of inputs means that we want the derivative of f1 with respect to the first variable, x1. So that's a single valued function. And then in the next column, I would like the derivative of that function with respect to the next variable. And of course, I'm going to have n of these derivatives because I have n variables. So I'm at the end going to have the derivative of that function with respect to xn. Okay, and then I could do the same thing for the derivative of f2 with respect to the vector x. And as you might guess, that's going to look very similar, except it's going to be the derivative of f2 with respect to x1, the derivative of f2 with respect to x2, all the way up to the derivative of f2 with respect to xn. Okay, each of these, notice, is a 1 by n. So one row by n columns, one row by n columns. And then, of course, you can kind of imagine that what we would have is we would have all the way up to the derivative of our mth function, fm, with respect to the vector x. And you guessed it, it's going to look exactly the same, fm with respect to x1, the derivative of fm with respect to x2, all the way up to that derivative of that function with respect to the last variable. Okay, that's a 1 by n. But notice that if we wanted to put this all into one matrix, one array, then we have a total of m rows of derivatives, n columns of derivatives, right? Here we are going to have n columns of derivatives. So if we wanted to pinpoint what is the derivative of f with respect to the vector x, okay, now thinking in terms, so what we did is we broke it down to the scalar level. Each one of these is an individual function, and we want to create the collection of them, right? We want to know, okay, well, what would this matrix of derivatives be? Well, in general, if f has m functions and n variables, have the partial of f1 with respect to x1. So basically this whole first row, I won't even list more than one component in that row because we know it's just going to have all n derivatives for f1. And then all the way down to fm, derivative of fm with respect to the first variable, all the way over to the derivative of fm with respect to the nth variable. There's our matrix, and then these will all be with respect to the nth variable. And then you notice that going along the diagonal, we're also going to have stuff there, right? So if we think about how big this is, we said it's m rows, so it will be m by, getting kind of colorful here, m by n, right? Because we're going to have n of those columns. So to summarize this df dx, given our circumstances, will produce an m by n matrix. I often write it like this, with just the subscript of m by n, or you can write it like this. You can say that df dx vector is an element of, or lives in, r m by n. Okay, so that stands for everything's a real number. We're in the domain of real numbers, but we're going to produce a m by n matrix of real numbers. All right, let's take a look at this in terms of an example where our function involves taking a vector containing two variables multiplied by this matrix A, and let's suppose that we want to find its derivative. So first of all, let's think about what our function is and what our variable x is. So what I'm going to do is I am going to actually list out what this function looks like in terms of our matrix, which just contains these constant coefficients, multiplied by our vector x1, x2. So the first element, if we recall matrix multiplication, multiplies the first column. The second element here multiplies the second column, and those two results get added together. So that will look like this. It will be x1 multiplied by the first column, 5, 2, 3, plus x2 multiplied by the second column, which is negative 8, 1, 4. And notice that really x1, if you think about it, yeah, it's x1 times the first column and x2 times the second column, but also it really amounts to 5x1 minus 8x2. 5x1 minus 8x2. And the second row would be 2x1 plus 1x2. And the third row would be 3x1 plus 4x2. So we can think about this as scaling the columns and then adding the results together, or we could think about them as scaling the row elements and then adding the row elements together like we did here on the right-hand side. But what I'm trying to do here is I have actually, notice, 3 functions. I get an f1 here, that's a function. I get another function in the second row, and I get another function in the third row. Why? Well, because the function is this vector, and this vector is a 3 by 1, and from our notation up here, the vector, the number of rows that it has, is the number of functions that we are dealing with. So we're going to define each of these to be functions. And, well, if we have, notice we have 3 functions and 2 variables. So using our nomenclature over here, we had m functions and n variables. That produced an m by n. So we are actually going to end up with the derivative of our function with respect to all of our variables. We're going to end up with that being a matrix that lives in 3 by 2. It's a 3 by 2 matrix. Let's actually go ahead and compute them. So what do we know about the partial of f with respect to x? Well, what we know is that in the top left column, or in the top left element, that's going to be the derivative of f1 with respect to x1. So here's f1. Take its derivative with respect to x1. Well, that means we're holding x2 constant, and the derivative of 5x1 is 5, and the derivative of negative 8x2 is 0 because we're holding x2 constant. So this is just going to be 5. And now in the second element, we need the derivative in the same row, the derivative of that same function with respect to x2, which will just be negative 8. Now in the next row, the derivative of f2 with respect to x1, which will be 2. The derivative of f2 with respect to x2 will be 1. And then down here, we'll have 3 and 4. So once again, just notice that this is the partial of f1 with respect to x1, partial of f1 with respect to x2, partial of f2 with respect to x1, partial of f2 with respect to x2, finally partial of f3 with respect to x1, and partial of f3 with respect to x2. And there we go. That is a direct application of working with vector-valued functions and computing their gradients. Okay, so notice that really all a gradient matrix is it's a gradient corresponding to each of our functions. So we have the gradient of f1 in the first row, gradient of f2 in the second row, gradient of f3 in the third row. So I will further, just so we're familiar with this, I will write this first row is the gradient of f1. Okay, and I'm going to put these little dashes here to indicate that that's a row. And this right here, this row will be the gradient of f2. And this row right here will be the gradient of f3. And that's pretty much how working with this will go. Now, just to practice this notation, let's map this out a little more generally. Okay, we're gonna write A in terms of its component here. So A is an m by n matrix. And the way I'll go ahead and write this is sometimes you use lowercase letters and sometimes you use capital letters. It really doesn't make a big difference, but I'll just label these A11, A12, all the way up to A1N. Okay, A is an M by N matrix. That means it has N columns, 1, 2, all the way up to the nth column. Second row will be A21, A22. Notice the subscripts tell you row column. So 22 would mean second row, second column. And then I'm all the way up to A2N. Now this will keep going. So we'll go down to the mth row, AM1, all the way to AM2, all the way over to AMN. It'll look like this. Okay? Now that's the way I can write it. Another way that I could write A is in terms of just its rows. This is M by N. It has M rows and N columns. I could abbreviate this a little bit and I could say that since the first index represents the row number, then I will just do kind of like my row notation like above, and I'll call this A1. I'll call this whole row A1. Now it's a row vector. A1 is a row vector, meaning it's a row of elements, not a column of elements. And then I'll do the same thing for A2. A2 will be another row, all the way down to AM will be another row. Okay, this is just one way to write it. You could also express it in terms of its columns, but we're going to do it this way for now. And now the question is, well, what would a function look like? What would one of the outputs look like? Well, F1, and remember x in this case is an n by 1, so let's also put that down. It's an n by 1. And xn by 1 will just be x1, all x2, all the way down to xn. And f1, all right, what will f1 be? Well, f1 of x is just the first function that we get from this multiplication of this matrix by this vector. So the way that I could think about this is notice that here I actually have, if I really think about this, this is an m by n matrix. And when these values get multiplied together, this vector here, A1 is going to be a 1 by n vector. 1 by n vector, all the way down to this being a 1 by n vector. So each of these rows has n elements in it, right? All n of these elements right here, that corresponds to just this row. Okay, when we multiplied earlier, what I was trying to get us to observe is, yes, we are taking the of the vector and scaling the columns by those elements and then adding them together, but also a way of thinking about it is that what we get here is we could think about 5, negative 8, x1, x2 as producing 5x1 minus 8x2. So think about this as the vector x1, x2 times the row 5, negative 8, resulting in 5x1 minus 8x2. That's actually a dot product. We're taking a 1 by 2 times a 2 by 1 and getting a 1 by 1 element. 5x1 minus 8x2 is a single number. That's a 1 by 1 element. Another 1 by 1 element. Another 1 by 1 element. So I'm going to go ahead and write this in the following way. I know that this is going to be the row vector A1 multiplied by the column vector x by the vector x. Okay, so what that's going to result in is that's going to result in these elements x1 through xn multiplying a11 through a1n. So that's going to look like this. It will be a11 times x1. Okay, so it's that element times a11 plus a12, that element times x2, plus all the way up until we get to a1n, which is this last element, times the last element of our vector, xn. Okay. Well, notice exactly the same thing that we came up with up here. It just, we were dealing with numerical size. We had a 3x2 and a 2x1. Now we're just making it more general, right? So there's n variables in this first equation. So again, what we could do is produce df1 with respect to x, and let's write that vector. Well, since we have n variables, this is going to be a 1 by n vector of derivatives. So first of all, if you take the derivative of this guy with respect to x1, all you get is a11, right? Because the derivative of a constant times x1 with respect to x1 will be the constant, and then all of these other variables are being held constant, so their derivatives are 0. So now, take the derivative of this thing with respect to x2. Well, all of the other derivatives will be 0, and you'll just be left with a12 times x2. The derivative of that will just be a12. And then all the way down to, when you take the derivative with respect to xn of this whole thing, you're just going to get a1n. And you can kind of imagine where we're going with this. If you go to last function, df with respect to x, well, that's just going to be the derivative of the bottom row times the vector, which will produce a similar expression like f1. It just, all of these will be m1, m2, mn, and therefore you will get a m1, a m2, all the way over to a mn. Again, is a 1 by n vector, and altogether df vector dx will be the full matrix where each row will be the gradient of f1 all the way down to the gradient of fm. That will just look like, in our context, with the matrix a11, a12, all the way over to a1n, down to am1, am2, all the way over to amn. So essentially, for a matrix full of constants, like this one is, the derivative of ax is just going to be a. And this is precisely what we get when f x is equal to ax for constants in A, then the derivative of f with respect to derivative of x vector will just be the matrix A. Pretty cool stuff.